Have you ever watched a video of a robot learning to walk and wondered, how on earth does it do that? There's no instruction manual. Well, today we're going to pull back the curtain on how an AI can learn something incredibly complex, all by itself, through pure trial and error. So let's just frame the problem. How does an AI go from knowing literally nothing to mastering a skill? I mean, imagine a brand new robot. How does it learn the insane dance of balance, physics, and movement required to take even one step without any pre-programmed instructions?
To really get our heads around this, we first need to understand that there's more than one way for an AI to learn. This will show us exactly why learning from your own mistakes is so incredibly powerful.
You can basically boil it down to two main approaches. On one hand, you have imitation learning. This is pretty much what it sounds like. The AI watches an expert and just copies what they do. It's straightforward. It works. But you have a hard ceiling. The AI can never get better than the teacher it's copying. But on the other hand, you have reinforcement learning. This is where the AI teaches itself. It learns from its own experience through trial and error. This is where things get really exciting, because this AI can actually become better than any human expert and even discover brand new strategies we've never thought of.
Okay, so when we talk about training an AI, what we're really saying is that we're trying to improve its policy. Now, don't let the term scare you. A policy is just the AI's current strategy. It's like its brain or its set of instincts at any given moment. It's the thing that decides, should I lift my left leg or my right? Our whole goal is to find the best possible policy.
But if the AI is all on its own, how does it know a good move from a bad one? Well, the answer is actually rooted in a really simple but powerful little loop.
This is the absolute core of the process. Step 1. The AI just tries stuff out. It runs its current policy and sees what happens, collecting data. Step 2. It takes that data and uses it to update and improve its policy. And step 3, you guessed it, repeat. Over and over and over, getting a tiny bit smarter each time.
So, how does it actually improve? The basic idea is super intuitive. It's the core of a family of algorithms called policy gradients. The AI just thinks, okay, that series of actions got me a really high score. Let's do more of that. And those other actions that led to a terrible score, yeah, let's do less of those. Simple, right? Well, as we're about to see, this simple logic can go wrong in some really surprising ways.
Okay, let's get back to our robot and see how this plays out in the real world. Because that simple rule has a critical and pretty funny flaw.
All right, here's our setup. A robot is trying to learn to walk. The only thing it gets a reward for is moving forward. Since it's starting with a totally random policy, its first few attempts are going to be, well, let's just say they're not very graceful.
So let's look at the results of its first few tries. It falls backward, gets a negative reward. It just stands there and does nothing, gets a 0. But then, in one attempt, it just kind of lurches and face plants, but hey, it moved forward a little bit. So for that, it gets a small positive reward.
Okay, so let's just pause here for a second and think about our rule. Do more of what gets a positive score. Looking at this data, what do you think the robot is going to learn to do next?
And here is the hilarious and brilliant problem. The AI learns to get better at falling on its face. Why? Because out of all its clumsy first moves, falling forward was the only thing that gave it a positive score. You have to remember, the AI has no concept of walking. All it knows is positive number, good. It found a cheap trick to get points, and it's going to optimize for that trick. This is a classic problem. The learning signal is just too noisy and can be totally misleading.
So clearly, our basic learning rule needs an upgrade. We have to help the AI see the bigger picture and not get fooled by these cheap, misleading rewards. And there are two really clever ways to do just that.
The first upgrade is just plain old common sense. Causality. An action you take right now can only affect the future, right? It can't change the past. So the AI should only judge an action based on the rewards that came after it happened. This helps it assign credit much more accurately instead of just rewarding everything that happened in a successful run.
But that brings us to the next big problem. Let's say our robot is actually getting better. Now, some of its attempts are clumsy stumbles, some are decent walks, and every now and then it manages to run. All of these things involve moving forward, so they all get a positive reward. So how does the AI learn to prefer running, which is obviously the best, over just stumbling?
So let's say it pulls off a decent walk and gets a reward of plus 50. That seems pretty good, doesn't it? But as we're about to see, good is all relative.
So let's ask the question a little differently. The robot just finished a try and it got a score of 50. Should it be encouraged to do more of that? Is plus 50 actually a good score?
And this is where context becomes absolutely everything. If on average just stumbling around gets you 20 points, then yeah, 50 is pretty good. It's an improvement. But what if the average score for a successful run is 100 points? Suddenly that 50 for walking doesn't look so hot anymore. It's a positive outcome, sure, but it's way below what's actually possible. We shouldn't be reinforcing it as strongly as we reinforce running.
This brings us to our second huge upgrade, using a baseline. A baseline is just a reference point. Usually it's the average reward the AI has been getting lately. By subtracting this baseline from its current score, the AI can figure out if an outcome was just kind of okay, or if it was truly better than average. This is the key to cutting through the noise and focusing the AI's learning on what really works.
And this gives us our brand new, much more powerful rule for learning. It's not just about getting a high score anymore. No, it's about getting a score that is better than you'd normally expect. This one simple shift from just positive to better than average is a total game changer. It dramatically reduces the noise and helps the AI lock on to the best possible strategies much, much faster.
Okay, so let's put all these pieces together and take a look at the big picture of what this powerful, if imperfect, approach to learning gives us.
So this whole method we've been talking about is called policy gradients. At its heart, it's just a formalized, smarter way for an AI to learn through trial and error. The core idea is to reinforce actions that lead to better than average outcomes. Now, even with our clever upgrades, the process can still be noisy, and it's on policy, which is a fancy way of saying it needs a constant stream of fresh data to learn from.
So why does all of this matter? Because this fundamental idea, learning from trial and error by reinforcing what works, is a cornerstone of modern AI. It's what allows robots to learn to walk and manipulate things. It's behind the AIs that can master incredibly complex games. And believe it or not, variants of these very ideas are used in training the massive, large language models that are changing our world today.
And all this brings us to one final and absolutely crucial question. If an AI is just learning to maximize a score we give it, how do we design those rewards to make absolutely sure it learns the lessons we want it to learn and not some clever unintended loophole? The entire future of safe and beneficial AI might just depend on how we answer that. Thanks for watching.